Now, on the left, we have a set of equations that describe the Kalman filter. Um, the parameters A, B, H, all of those are common parameters that have to deal with the mathematical model or how that model translates into what we're measuring, but they can be a little bit difficult to understand, especially if you're seeing them for the first time. So I want you to look at the equation on the right, which is a little bit simpler. So x of k, that's a vector, and that vector, it describes each measurement that we're trying to analyze. So say we're trying to track the baseball. We might want to know four parameters: the position of the ball, the x position of the ball, second the y position of the ball, and then the velocity in the x and y directions, respectively. So that would be a four-column vector. Now we have, let's skip over the Kalman gain, we'll get to that, but we have a measured value. Now, this is the value that we would get from our measurements from our foreground detector. And then further on to the right, we have what's noted as previous estimation, and that's going to be the value that the mathematical model gives us. So this equation, it's a weighted average, and it averages the measurement data that we get and what the mathematical model says, and then uses this common gain factor to calculate which one I should rely on more. Now, the common parameter ranges from as a value from 0 to 1. So in this case, a value of 1 means we only use measured data. We're not going to use a mathematical model. A value of 0 means we're going to use just a mathematical model and not use the measured data. And any value in between is, again, a weighted average of the two. Now, knowing this in mind helps us understand why we want to use Kalman filter. And so let's think of extremes. Say that the common gain was 0. If the common gain was 0, that means that we ignore measurement data and we just use the previous estimation, or we use the mathematical model. So when would we only want to use mathematical model data? Well, say that we had data dropout. Say that we had no measured data, or our measured data was so off the wall that it obviously had to be wrong. Well, then the algorithm could switch over to mathematical model mode and predict where the ball would be. Go back and imagine when the ball was shot from the cannon, we're recording it, and then the camera blanks out, doesn't record anything for a second or so, and then comes back on. I don't know where the ball was during that data dropout, but with the mathematical model, I can get a pretty good guess. So let's look at the flip side. Say that we had a common gain of 1. That means that we only look at measured data. This would happen in a case where our mathematical model is completely off. Something happens that's unexpected, that doesn't fit into the model, and so we just ignore that and we say, I'm going to stick with the measured data. An instance of this would actually be whenever the algorithm starts up. The mathematical model needs certain inputs. If you think of projectile motion, you need initial velocities. And so that model might not get it, in the beginning. So in that case, we would just take measured data and just use that. Just use the measured data until we're able to use model data. And that's just one example. So going forth, this is the process that I took to model to track moving vehicles and the way to model it. Now, I broke this up into two parts. The first part was trying to track a Gaussian blob. Now, a Gaussian blob is simply what you would think of it as. It's a blob that's that in terms of images is 1 in the center, it's pure white, and then it kind of slowly fades off to be 0. If you look on the image on the top right, you'll see a white rectangle and then a blob off to the right, and then that's what the Gaussian blob looks like. The white rectangle is, I'll explain why that's there later. So the goal was to create a blob moving across the screen, and then take that video and put it into the foreground detector, and have the detector detect where that blob is. Then take that, put it into the Kalman filter, and then see which one is able to track it better. The good news is with this is since the video is created and it was created in MATLAB, we know the exact center of the blob, so we can see which one's more accurate. And then finally, generate error statistics. Now, before I get into step 2, I want to discuss the white rectangle. There's two things that I wanted to look at when tracking the Gaussian blob. Number one is what happens in a noise-free compared to a noisy background. If you look at the top right image, there's obviously a noisy background. So I wanted to see how well can we track that blob in a noisy environment. And secondly, how does the algorithm perform under data dropout conditions? In this image, it's obviously not a video, but the blob would begin in the left and pass through the white rectangle, and then it would disappear, and then it would come back out on the other side. So we're not able to detect with a foreground detector where that blob was, but we can use a mathematical model to guess where it was, and we're going to see later how well that performed. Now, continuing to step 2, we would ideally like to do the same thing as step 1. Get video footage of a moving car, put that video into a foreground detector to detect where the car is, and then put that through the Kalman filter and see which one performed better. And on the bottom right is a screenshot of the video I chose. It's of a truck moving across the screen. So let's get into step 1. And before we get into the results, I'm going to just talk about the videos that were made. So I made 4 videos of a Gaussian blob moving across the screen under 4 conditions. The first was a noise-free, no data dropout condition. Now this is about as simple as we can get. We have a blob and it moves in a direction. There's no data dropout, it doesn't disappear, and there's no noise. This should be the easiest video for the algorithms to track. The next is a noisy video, but with no data dropout. And this is like the screenshot that you see on the top right. It's noisy, like we see. The third was a noise-free condition, but with data dropout. And then finally, a noisy condition that does have data dropout. And then that would be when the blob passes through the white rectangle, and again, it's all noisy, it's hard to detect. Now, just a little bit more information. These videos were about 100 frames long, and the blob moved at a constant velocity of 10 pixels per frame. Again, the idea of tracking Gaussian blobs instead of vehicles was to just make sure that the algorithms work, just to check them and then move on to vehicles. This presentation will continue in the next video.